All right, so this video is going to be about torque and a couple of different types of torque. All right, so if you rotate something, so forces with equal strength will have different effects on a door. So here's your hinge. So this rotates around this position. The ability of a force to cause rotation depends on your amount of force and the distance the force is from the pivot point. Okay? We're looking at it causing rotation. And it also depends on the angle from the door at which the force is applied. And you look at this thing called torque. So torque is not a force. Torque is the result of a force. And more specifically, it's the torque is due to the force that's perpendicular to whatever you're moving at a distance from the pivot point. So if you think about it, the farther you are away, if you have equal forces acting perpendicular on an object, the farther you are away, the more torque you apply or you create. So like if all these forces are equal, actually this one right here, F2, would give you the least amount of torque because none of it's perpendicular to the door. Between F1 and F4, if F1 and F4 are the same force, F1 is going to create the greater amount of torque. All right, so we have something called the radial line. It's a line that starts at the pivot point and extends out through the point where a force is applied. So this little line with an R on it is your radial line. The angle is measured from that radial line to the direction of the force. So right now you have this little angle. Ideally, to get the greatest amount of torque out of this, you want this angle to be 90 degrees. Okay, so again, the radial line is the line starting at the pivot point, extending through the point where the force is applied. Angle is measured from that line. And torque is dependent on the perpendicular component of that force being applied. So here's our total force. We're looking for the vertical, the perpendicular component, which would be your total force times the sine of your angle. The parallel component out to the radial line does not create a torque. All right? So we can look at this in terms of what's called the moment arm. The moment arm is the line perpendicular distance from the line of the action of the pivot. So you have the force, and this action line goes this way. Okay. There's your line of action. Here's what's called your moment arm. So if you can think about, we have this nice right triangle with your radial line, the line of action, and the moment arm. The moment arm is the bottom component of that right triangle. So if we look at that torque due to a force with a moment arm, it's your moment arm times your force. Essentially, it's the same idea. So for both methods of calculating torque, it's the same expression. Torque is equal to radius, or either the moment arm or the radial line, times the force times the sine of your angle in relation to the line. Okay. All right, so we have the sample problem here. We're trying to open a door. Ryan pushes it at a point 75 centimeters from the hinge with a 240 Newton force directed 20 degrees away from the perpendicular. Okay, there's a natural pivot point, the hinge is. So what torque does Ryan exert? And how could he exert more torque? So here's what we have. We have our pivot arm. We have our force, and we have the angle that it is from the perpendicular. Okay, so, and because we need to find the perpendicular component of the force, since we know this angle this time, the force that we apply, the perpendicular force, is your force times your cosine of theta, because now we have the adjacent leg. So 240 times the cosine of 20 is 226 newtons. So that's the force used to make the object move. So we then solve the torque applied. Okay, so your lever arm, 0.75 meters. The force applied, 226 newtons. The torque is 170 newton meters. Okay, and if he wants to exert more torque, a couple different things. If he's just going to use that amount of force, he can go further out before he hits the edge of the door, or he can try to go perpendicular. All right, so we have another sample problem, and this has been actually seen in history a couple different times. People overthrow a certain leader, and they tie a rope on its head. The statue is 17 meters tall, and they pull with a force of 4,200 newtons at an angle 65 degrees to the horizontal. What's the torque they exert on the statue? If they're standing to the right of the statue, is the torque positive or negative? Okay, so the component of the force that's perpendicular to the lever arm, which is the statue, is 4,200 newtons times the sine is 65. How did we get 65? 65 degrees to the horizontal. Okay, so horizontal, kind of imagine it's 65 degrees down. So we're looking at the sine of that, which is 3,800 newtons at a height of 17 meters from the pivot point. So 3,800 times 17 is 6.5 times 10 to the 5th Newton meters. So if you're standing to the right of the statue and pull it towards you, the statue will fold to the right, which would make it counterclockwise. Okay. All right. This is all about the perception piece. Okay. All right. So we found our component force. We made our torque. All right. A torque that tends to rotate the object counterclockwise. Again, torque is the result of a force. It's not a force. All right. So perpendicular positions are the spot where you have the most torque, where you can create the most torque with the force. If it's parallel to the radial line, you get no torque. All right. So if you have a bunch of different forces acting on an object to make it spin, you can create a net torque. I do apologize for my hiccups. Okay. The angle exerts a force on... So the axle exerts a force on the crank to keep a net force of 0. Okay, so you could figure out the sums of these. If you knew all the forces and you knew their angles from the lever arm, you could figure out the net torque. All right, so now we're going to take this and look at it in terms of center of gravity and torque in large situations. Okay, so if we look at this little gymnast here, gravity pulls every little particle down. Each particle experiences a torque due to gravity if it's rotating. So here's your rotational axis. There's a torque acting on all of these little locations. So the gravitational torque can be calculated by assuming that the net force of gravity acts at a single point. This single point is called your center of gravity. So this is like where most of the weight is concentrated. The gymnast responds as if her entire weight is acting at her center of gravity right here. So then basically this is your average where most of the weight is going to be pulling you down. So this is your force. You have your lever arm to create the torque. All right, so if we have something like a flagpole, okay, we have a force pulling down, 33.2 kilogram flagpole extends from a wall at an angle of 25 degrees from the horizontal. If the center of gravity is 1.6 meters from the point where the pole is attached to the wall, what is the gravitational torque on the flagpole about the point of attachment? So we have this situation set up here. We know our angle. We know how far our force is from the pivot point. We can figure out the torque because we know the mass of the object. Okay. We see that the moment arm is 1.6 meters. Okay, 1.6 meters times the cosine of 25, because we know our angle. We're going to figure out the moment arm here. And we know that our moment arm is 1.45 meters. So torque is going to be your force, which is your weight of your object, times your moment arm. So 1.45 times 3.2, which is your mass, times acceleration due to gravity, is negative 45 newtons. Negative 45 newtons because it's rotating it in the opposite direction that this angle is applied. Okay. All right. So an object that's free to rotate around a pivot point will come to rest with the center of gravity directly below the pivot point. You want to have your center of gravity in line with your pivot point. If something freely rotates, the center of gravity is going to be directly below it. Just like it shows it back there. If you take a ruler and hold it, when it swings, it's going to stop with the center of gravity right below the pivot point. When we talk about things falling over, they fall over when the center of weight exceeds a point of balance, so it has a point to pivot, and it's going to fall. And then your center of gravity will be below your pivot point when you rotate, when you topple over. Okay, so torque due to gravity when the pivot is at the center of gravity. We can use this to find the expression for the position of the center of gravity of other objects. So keep in mind that we have this torque idea. All right, so for this dumbbell, the pivot must be at the center of gravity. The pivot point. We can calculate the torque on either side of the pivot, which is located here. You think back kind of like the center of mass. This pivot point is going to be closer where there's more mass. The torque due to the weight on the left side is this. So we have on the left side, we have our mass. We have our moment arm. And the torque on the right is our other moment arm times the weight, times this weight. The total torque then is, you add these two, but really it's a subtraction problem because they're going in opposite directions. Okay. So the location of the center of gravity then is found by this equation, and you're going to want to write down this equation for the center of gravity because it's a big important thing. The location of the first one times its mass plus the location of the second one times its mass plus the sum of the masses. It gets you your center of gravity. This is an important equation. Okay, so because the center of mass depends on the distance and the mass from the pivot point, objects with large masses count more heavily, so it moves the pivot point closer to them. All right, so you can As we mentioned, you can use to find the center of gravity. You're using these two equations. Make sure you jot those down, they're important. Okay, so a 1 meter long dumbbell has a 10 kilogram mass on the left and a 5 kilogram mass on the right. Find the position of the center of gravity, the point where the dumbbell should be lifted in order to remain balanced. So we have this. So the length is a meter. We know the center of gravity is going to be closer to the 10 kilogram object because it has more mass. So if we put the 10 kilogram object at the 0 mark, the 5 kilogram object is going to be at the 1 meter mark. Okay. So then we can figure out what our distances are going to be. We just have to figure out how far apart these are. And since we know how far apart they are, the 10 kilograms at 0, the 5 kilograms at 1, 10 kilograms plus 5 kilograms, so it's the locations in the coordinate system. We can figure out where the center of gravity is. So really it's 5 divided by 15, or a third of a meter. So center of gravity is a third of a meter in between. All right, so that's the end almost of video 1 or video 2. Make sure you fill out the Google form and answer the questions, and ask questions if you have them, and we will talk about them in class. See you in class.